What if the Big Bang was not the true beginning of everything? What if space, time, and matter were only the first visible layer of a much deeper reality? For years, science has traced the universe back to its earliest light, its first atoms, and its first moments of expansion. But the closer the search gets to the beginning, the stranger the story becomes. Some physicists believe the Big Bang may have emerged from a quantum vacuum, a dying universe, a hidden cycle of reality, or something even harder to imagine. In this video, the journey goes beyond the birth of stars and galaxies into the mystery of what may have come before time itself. Before getting started, please take a moment to like the video, subscribe to the channel, and share it with someone who loves cosmic mysteries. Thank you so much for watching and for spending time here. It would also be lovely to know what time is it where this is being heard, and from which part of the world is it being heard tonight now. Let us begin. The universe first appears not as a place but as a question. It hangs behind every measurement, every telescope image, every map of distant light. Human beings learn to look farther and farther into space, and in doing so they also look backward through time. The deeper the view becomes, the stranger the picture grows. Great observatories circle Earth or rest beneath dry desert skies, gathering faint signals that have crossed unimaginable distances. Hubble reveals ancient galaxies as soft traces from an earlier cosmic age. James Webb pushes deeper still, finding bright and surprisingly mature systems of stars in epochs once expected to be simple and raw. The European Southern Observatory tracks motions in distant structures. NASA and ESA piece together a history written in redshift, background light, and the slow retreat of galaxies from one another. Each new instrument sharpens the scene. Each improvement makes the beginning feel less settled. The broad outline seems clear at first. Space expands. Galaxies drift apart. The farther away a galaxy is, the faster it appears to recede. This pattern suggests that the universe was once hotter, denser, and smaller than it is now. The cosmic microwave background, discovered in the middle of the 20th century and later mapped in exquisite detail by missions such as Wilkinson, Microwave Anisotropy Probe and Planck, preserves a faint afterglow from an early era when the universe cools enough for light to travel freely. The chemical makeup of the cosmos also points in the same direction. Hydrogen dominates, helium follows, tiny traces of lithium remain. These proportions fit a universe that begins in an intense furnace and then rapidly expands. For a long time, this picture seems to answer the greatest question ever asked. It seems to explain how everything begins. Then the edges start to fray. The Big Bang does not describe an explosion inside empty darkness. It describes the expansion of space itself. That distinction sounds neat and satisfying until the mind presses against it. If space is expanding, what is it expanding into? If time begins with that expansion, what does before even mean? If all known matter and energy are compressed into an almost inconceivably dense state, what sets the stage for such a state to exist at all? Physics traces events back with impressive confidence through the first minutes, then the first seconds, then fractions of a second so small that ordinary language starts to fail. Yet the closer the account moves toward the first instant, the more the firm ground of explanation gives way beneath it. The beginning remains visible only from a distance. Up close, it becomes a blur. This is where the mystery deepens rather than retreats. Modern cosmology is often presented as if it has already crossed the hardest threshold, as if the oldest mystery has been replaced by numbers, timelines, and technical names. In one sense, that is true. The age of the observable universe is estimated at about 13.8 billion years. Its large-scale geometry appears remarkably flat. Dark matter shapes galaxies through gravity, though it has never been directly seen. Dark energy seems to drive the expansion faster over time, though its nature remains obscure. Black holes anchor galaxies. Supernovae mark the lives and deaths of stars. All of this is known well enough to build a cosmic story with confidence, yet the central wound in that story never fully closes. The story begins after the beginning has already happened. Even the word beginning becomes unstable under pressure. In ordinary life, a beginning is easy to imagine. There is first a state in which something is absent, and then a state in which it arrives. A room is empty, then it is occupied. A page is blank, then it is written. A starless sky turns and brings dawn. But these examples all depend on time already existing, space already existing, and rules already being in place for one condition to change into another. The beginning of the universe may not belong to that category at all. It may not be an event inside a larger background. It may be the appearance of the background itself. The mind reaches for familiar patterns and finds nothing solid to hold. Astronomers do not stop at that boundary. They keep collecting clues from the visible aftermath. When James Webb peers into the deep past, it does not photograph the beginning itself, but it shows galaxies shining when the universe is only a small fraction of its current age. Some appear larger, brighter, or more structured than older expectations suggest. These findings do not overthrow cosmology, but they complicate it. They hint that the early universe may organize itself faster than simple models predict, or that unseen ingredients have greater influence than once assumed. Elsewhere, measurements of the present expansion rate do not always agree cleanly with values inferred from the early universe. This tension is subtle, technical, and still under debate, yet it matters. It raises the unsettling possibility that the standard account is either incomplete or missing some hidden factor. If the present and the ancient past refuse to fit neatly together, the opening chapter may be stranger than expected. The same unease appears in the dark components of the cosmos. Ordinary matter, the matter of stars, planets, gas, dust, bodies, oceans, and stone, seems to account for only a small fraction of the total cosmic budget. The rest lies in unseen forms. Dark matter reveals itself through gravitational pull, holding galaxies together more tightly than visible mass alone can explain. Dark energy reveals itself through acceleration, pushing the large-scale universe apart faster as time goes on. These names sound descriptive, but they are really markers of ignorance. They label effects more than causes. The universe behaves as though most of its substance is hidden, and most of its long-term fate is driven by something barely understood. That fact changes the mood of every origin story. If the universe is already built mostly from unknown ingredients, then any confident claim about its ultimate beginning becomes less secure. There is another problem, quieter and more profound. The equations of physics are often excellent at describing how a system evolves once it exists. They tell how stars burn, how particles interact, how light bends near gravity, how space expands under certain conditions. But a law that describes change is not automatically a law that explains existence. A rule can govern what happens next without revealing why there is a stage, a set of actors, or any rule at all. This gap becomes easy to hide inside elegant mathematics, but it never disappears. The deepest theories may one day join gravity and quantum physics into a single framework. They may describe the first meaningful moment with astonishing precision. They may even show that the earliest universe arises naturally from some prior state. Yet each step backward invites the same silent pressure. What gives rise to that prior state? What allows reality to be structured in any way rather than absent altogether? Speculative ideas emerge from this pressure almost inevitably. Some suggest that the universe comes from a quantum vacuum, a state that appears empty but is not truly nothing. Some imagine a prior cosmos collapsing or fading and somehow giving birth to a new expansion. Some picture eternal cycles, where every ending becomes another opening. Some widen the frame into a multiverse, where this universe is one region inside a far larger reality. Some even wonder whether time itself is not fundamental, and that what is called before the Big Bang is not earlier in the ordinary sense, but deeper. None of these possibilities are simple guesses. Each is anchored in some feature of known physics, some observed pattern, some mathematical path that seems worth following. Yet none removes the mystery. They move it. They reshape it. They often make it larger. So the universe stands revealed in two layers at once. On one level, it is measurable, mapped, dated, and increasingly precise. On another, it is still profoundly unresolved. Telescopes gather more light, satellites refine more data, computers simulate cosmic evolution across vast spans of time. And still, the oldest question remains curiously untouched at its core. Not because nothing is known, but because what is known keeps pointing toward a threshold that refuses to become ordinary. The beginning is no longer a blank space in thought. It is something more unsettling. It is a place where knowledge grows sharper and certainty grows thin, where every new image of the early cosmos seems to whisper that the first mystery is not disappearing at all. It is merely changing shape. If the universe is followed not as a philosophical puzzle but as a physical sequence, its earliest history does not begin with stars or galaxies or even atoms. It begins with heat so extreme that ordinary matter cannot survive inside it. The familiar world of stable things does not exist there. No planets form. No light crosses open space in the way it does now. No atom can keep its structure. The early universe is less like a place and more like a condition, a changing sea of energy and interaction, where the ingredients of later reality are present only in broken, temporary, or unfinished form. This is one of the first unsettling truths hidden inside cosmology. The universe that eventually becomes rich with structure starts in a state that has almost none of the features usually associated with existence. The standard timeline, when read closely, does not move from nothing straight into matter. It moves through layers of strangeness. In its earliest known moments, the universe expands and cools with extraordinary speed. During the first tiny fraction of a second, physics describes forces that may once have been joined in ways no longer visible today. As the temperature falls, symmetries break. Different interactions begin to separate from one another. Conditions change so quickly that the laws of nature themselves appear to be settling into the forms now observed across the cosmos. This account is precise in places and speculative in others, but its overall meaning is clear. The universe is not born ready. It passes through stages in which the rules and ingredients of later reality are still taking shape. For a time, matter as commonly understood does not yet exist. There are no protons or neutrons at first, only a turbulent swarm of more elementary ingredients in constant transformation. Quarks, gluons, leptons, radiation, and other fleeting participants crowd the scene. The heat is so intense that anything capable of being bound is immediately torn apart again. The universe is full, yet nothing in it can hold its identity for long. It is a reality of pure process. Particles appear, collide, vanish, and reappear. Matter and antimatter emerge in nearly equal abundance. Whenever they meet, they destroy one another and become energy once more. The whole scene behaves less like the orderly foundation of a future cosmos than like a ceaseless argument between existence and erasure. That violence matters because something very small and very strange seems to tilt the balance. If matter and antimatter had remained perfectly matched, almost everything would have annihilated almost everything else, leaving behind a thin bath of radiation with scarcely any material substance to build stars, planets, or living beings. Yet that is not what happens. For reasons still not completely understood, the universe appears to favour matter by a tiny margin. The difference is almost absurdly slight, a small excess buried inside overwhelming symmetry. But after the great mutual destruction runs its course, that tiny excess remains. All later structure depends on it. Galaxies, gas clouds, oceans, mountains, blood, bone, atmosphere, memory, and thought all descend from that minute imbalance. The universe as it is known seems to rest on a defect so small that it feels less like a design than a clue. Physicists search for the source of that asymmetry in the laws governing the early universe. Certain interactions are known to treat matter and antimatter differently under particular conditions. Experiments in particle physics have observed subtle forms of imbalance, yet the known effects do not easily account for the full cosmic surplus. Something in the first moments may have broken the symmetry more deeply than current models capture. That possibility opens a dangerous and fascinating space. It suggests that one of the most basic facts about the visible universe may depend on an event or process not yet seen directly. A hidden turn in the earliest physics that leaves only consequences behind. Matter survives, but the reason it survives remains partly obscure. The universe begins to look less like an inevitable outcome, and more like the survivor of a near cancellation. As expansion continues and temperatures fall further, quarks become confined inside protons and neutrons. Later still, within the first few minutes, atomic nuclei begin to form in a process known as primordial nucleosynthesis. Hydrogen nuclei emerge in vast numbers, helium appears in large amounts, a little lithium is produced. Then the universe cools too much for fusion to continue efficiently in that early form, and the composition is largely set. This is one of the great successes of cosmology, because the predicted proportions match what is observed on the largest scales with striking accuracy. The early universe leaves behind a chemical signature, and the signature fits the broad picture. Yet even here, in one of the clearest windows into the beginning, the mystery does not withdraw. These nuclei are still not atoms. Electrons still move through a hot plasma. Light cannot yet travel freely. The universe is opaque, glowing, crowded, and trapped inside its own brightness. Hundreds of thousands of years pass before atoms finally form. Only when the cosmos has cooled enough do electrons settle into stable orbits around nuclei. Then, at last, light decouples from matter and begins the long journey later captured as the cosmic microwave background. This afterglow is often treated as the first visible image of the universe, and in one sense it offers a baby picture of the cosmos, a map of tiny temperature differences spread across the whole sky. But even that phrase can mislead. By the time this light is released, the universe has already been evolving for a very long span in its own early terms. The first visible universe is not the first universe. It is only the oldest one that can still be seen directly. Everything earlier must be reconstructed indirectly, like a vanished landscape inferred from ash, shadow, and pressure marks. That hidden era contains another tension. It is not merely hot, it is astonishingly smooth. On the largest scales, the early universe appears nearly uniform in every direction. This is one of the strangest facts in cosmology, because distant regions of the young cosmos seem too similar to one another if judged by ordinary expansion alone. They should not have had enough time to exchange information or settle into common conditions, and yet they do. Inflation, the idea that the universe undergoes a brief period of extremely rapid expansion in its earliest moments, is one proposed answer. It explains why space looks flat, why the cosmos is so uniform overall, and why tiny fluctuations later grow into galaxies. It is a powerful idea, elegant and influential, but it also shifts the mystery rather than erasing it. What triggers inflation? What ends it? What field drives it? Why does it begin at all? The model clarifies the pattern, then leaves a new mechanism standing in the dark behind the pattern. The first atoms therefore do not arrive as the completion of a simple story. They arrive as the first stable islands in a history already full of unresolved thresholds. Before them lies the strange survival of matter for antimatter. Before that lies the separation of forces and the freezing of physical laws into their present forms. Before that lies a density and temperature so extreme that known descriptions begin to lose confidence. Each step backward makes the universe feel less like a machine that starts cleanly, and more like a layered emergence, with one form of order condensing out of another, each layer resting on a deeper one that remains partly hidden. This is why the question of what came before the Big Bang does not disappear when early physics is explained in detail. It becomes sharper. Stable matter does not exist at the start. Atoms come later. Nuclei come later than that. Protons and neutrons themselves emerge after still earlier transformations. The things that fill the present universe are assembled gradually from states that do not resemble them. The closer the story moves toward the source, the less the source looks like substance in any familiar sense. Matter is not waiting at the beginning like raw material in storage. It condenses out of a prior order that is energetic, unstable, and difficult to picture. Then the obvious question arrives with greater force than before. If matter is not primary, what is? If the universe begins not with objects but with conditions, where do those conditions come from? And if the first recognizable pieces of reality appear only after the cosmos has already been changing for some time, then perhaps the true beginning lies hidden behind a curtain more fundamental than matter itself. The story grows stranger the moment empty space enters the frame. At first, emptiness seems like the simplest idea in all of thought. It appears to mean the absence of everything, no matter, no light, no motion, no structure, no events, no hidden activity, just a blank. Yet modern physics does not allow empty space to remain that blank for long. The deeper it is examined, the less empty it becomes. The vacuum, in scientific language, is not a featureless void. It is the lowest energy state available to a field, and fields are not added decorations on top of reality. They are woven into reality itself. Every known particle is tied to a field. Electrons arise from one kind of field, quarks from another, photons from another still. What appears to be empty space is better understood as the stage in which these fields are always present, even when no stable particles are visible. That shift in meaning changes the tone of the entire origin question. If the vacuum is already a structured condition, then it is not nothing. It is a strange and restless something that only looks empty from a distance. This is not merely a poetic reinterpretation. It emerges from a long line of experiments and calculations that repeatedly push physicists toward the same conclusion. In quantum theory, the vacuum is alive with fluctuation. Energy does not sit perfectly still. Fields do not rest in absolute silence. Tiny disturbances arise naturally because the quantum world does not permit complete stillness in the ordinary sense. These disturbances can briefly produce particle-like excitations that appear and disappear before they can settle into stable form. Such events are often described in popular language as particles popping in and out of existence. The phrase is simple, but what it points to is profound. The emptiest known state of physical reality behaves like a place where reality never fully stops happening. Evidence for this hidden activity does not come from one dramatic image, but from several subtle effects spread across different domains of physics. The Casimir effect, for example, reveals that two metal plates placed very close together in a vacuum experience a tiny force, as though the vacuum between them is not the same as the vacuum outside them. The effect is small, but it is measurable, and it fits the idea that even the vacuum has structure and modes of fluctuation. Other phenomena, such as shifts in atomic energy levels and the spontaneous emission of radiation, also make more sense when the vacuum is treated as physically active rather than truly empty. In high-energy experiments, particles and antiparticles appear from collisions in ways that reflect field behavior rather than the movement of tiny hard objects through passive emptiness. Everywhere, physics looks carefully. The vacuum refuses to act like nothing. That refusal matters because one of the most common origin stories in modern culture says that the universe may have come from nothing. The phrase sounds bold, almost final. It suggests that science has reached a point where being itself can be extracted from non-being. But once the vacuum is understood more honestly, the claim becomes much less straightforward. A quantum vacuum is not an absence of law, an absence of structure, or an absence of possibility. It already contains fields. It already obeys principles. It already has a mathematical form. It already permits fluctuation. Even the phrase empty space quietly assumes the existence of space. And space is not trivial. Space has geometry. It can expand, bend, ripple, and carry energy. It can host fields. It can generate horizons around black holes and preserve relic radiation across billions of years. If something arises from a vacuum, then it does not arise from nothing in the deeper sense. It arises from a physical state whose hidden richness only becomes clear under careful examination. This is where the mystery changes shape. The question is no longer whether the universe can emerge from a blank void, because physics has not clearly found such a void anywhere. The question becomes whether the vacuum is fundamental enough to play the role of a beginning. Could a quantum vacuum exist before matter, before stars, before atoms, before any familiar cosmic structure? Could such a state fluctuate in a way that triggers an expanding universe? Some models suggest this possibility in cautious terms. They imagine an early condition in which a tiny region tunnels, fluctuates, or transitions into a new state with different energy properties, and that change drives rapid expansion. In these accounts, the universe begins not from absolute nothing, but from a pre-existing quantum condition that is unstable, fertile, or poised for transformation. This idea sounds less impossible than creation from nothing, because it works with concepts already active in modern theory, yet it leaves an older tension untouched. Why is there a vacuum at all? Why are there fields? Why should law, structure, and possibility already exist in silence before matter appears? The unease deepens further when the vacuum is linked to cosmic inflation. Inflation is proposed as an early burst of enormous expansion that stretches space so rapidly that microscopic irregularities become the seeds of galaxies. In many versions of the idea, a field trapped in a high-energy state behaves almost like vacuum energy and drives this expansion. Then, as the field relaxes, its energy is released into particles and radiation, filling the universe with the ingredients of later structure. This picture is compelling because it explains several otherwise puzzling features of the cosmos. It helps account for the universe's large-scale smoothness, its near-flat geometry, and the small fluctuations later seen in the cosmic microwave background. But inflation also carries a strange emotional consequence. It suggests that the material universe may emerge out of something closer to stored potential than to substance. Matter is not present at the start in anything like its current form. It is produced as a consequence of a field state and the release of energy. Once again, ordinary intuition is left behind. the universe begins to look less like a thing built from raw material and more like an unfolding transformation within a hidden sea of possibility. Yet the word possibility can be misleading. It sounds philosophical, abstract, almost detached from measurement. But in this context, it points to something physical. A field has possible states. A vacuum has allowed fluctuations. A region of space can occupy one condition and then transition to another. What seems unreal at one level may become real at another if the right thresholds are crossed. The early cosmos may therefore be described as a place where what can happen matters just as much as what already exists. In the quantum world, the boundary between those two is less sharp than everyday experience suggests. A particle does not always carry a single fixed path. A field does not remain perfectly calm. Outcomes are weighted, distributed, and only later settled into definite histories. This does not mean that anything imaginable happens without constraint. The quantum world has rules. It is disciplined, not chaotic. But its discipline does not resemble the clockwork certainty once associated with classical physics. It is a discipline of amplitudes, likelihoods, and restless backgrounds. The vacuum is lawful, but it is not static. From here, the origin question becomes more disorienting than before. Suppose the universe does emerge from a quantum vacuum or some related state. That would not mean the deepest mystery is solved. It would only mean the first stage of explanation moves one layer down. The real beginning would then lie not in the appearance of matter, but in the existence of the vacuum itself and the rules that govern it. And if those rules are described by quantum field theory, another problem appears immediately. Quantum field theory usually assumes a space-time background. It is excellent at describing particles and interactions within space and time. But if the question concerns the origin of space and time, then any account that already presumes their existence may be incomplete at the deepest level. The vacuum may therefore be too rich to count as nothing, and too dependent on prior structure to count as the final answer. It is closer to an intermediate mystery, a bridge between the familiar world and something still more hidden. This is why the vacuum feels so unsettling in the story of cosmic origins. It appears to offer a natural mechanism for emergence. It shows that physical reality contains latent activity even in its quietest state. It demonstrates that emptiness, when examined with sufficient care, is not simple absence. Yet every gain in understanding produces a loss of conceptual comfort. The vacuum explains too much to be dismissed and too little to bring closure. It is not the blank from which everything could cleanly appear. It is a dynamic condition whose existence already demands explanation. It holds fluctuating energy, lawful structure, and the power to generate effects. It is almost the opposite of nothing, and so the old question returns in a sharpened form. If empty space is already full of hidden activity, then what stands beneath empty space? If the quietest known state of reality is still crowded with possibility, then where does that possibility come from? And if the universe begins in a vacuum that is never truly still, then perhaps the first mystery is not how something comes from nothing, but why even nothingness refuses to stay empty. The trail back toward the origin eventually reaches a region where the usual tools of physics no longer fit cleanly together. Before atoms, before nuclei, before protons and neutrons, before the known forces settle into their current forms, the universe enters a domain so extreme that the two great frameworks of modern science begin to interfere with one another. General relativity describes gravity and the large-scale structure of space-time with remarkable success. Quantum mechanics describes the small world of particles and fields with equal brilliance. Each theory works with stunning precision in its proper range, yet at the deepest beginning, where the universe is both unimaginably dense and unimaginably small. Both theories are needed at once. That is where the trouble starts. The equations that rule the very large and the equations that rule the very small do not merge gracefully under those conditions. They both point towards something important, and together they refuse to form a complete picture. This threshold is often associated with what is called the Planck era, the earliest slice of cosmic history that current physics can point to without claiming real understanding. It lasts for only an almost absurdly tiny instant after the supposed beginning, far smaller than any interval that can be pictured in ordinary thought. In that interval, density, energy, curvature, and temperature rise towards scales where familiar descriptions stop behaving normally. Space is no longer obviously smooth. Time is no longer obviously continuous. Gravity is no longer just the slow warping of a stable stage. The stage itself begins to flicker. At that depth, it is not simply that the universe is hard to observe. It is that the basic concepts used to describe any observation may no longer apply in their usual form. The ordinary mind is trained by daily life to treat space as a container and time as a flow. Events happen somewhere, and they happen in sequence. One thing causes another because first comes before later. That intuition works well enough for clocks, roads, weather, orbiting planets, and falling stones. It even extends surprisingly far into astronomy. Galaxies collide, stars ignite, black holes merge, light travels, distances stretch with expansion. But in the earliest conceivable universe, those assumptions may all be secondary rather than fundamental. Space may not be a container at all. Time may not be a river running underneath events. Both may emerge from something deeper, something more granular, relational, or abstract than ordinary experience suggests. If so, then asking what happened before the Big Bang may carry a hidden flaw. It may assume a temporal background that does not yet exist. This possibility is not drawn from pure imagination. It rises from attempts to build a theory of quantum gravity, a framework that would treat gravity in genuinely quantum terms rather than as a purely classical geometry. Several approaches try to move in that direction. String theory suggests that the most basic ingredients of the universe are not point particles, but tiny vibrating entities whose different patterns of motion give rise to different particles. In such a framework, space-time may not be as fundamental as it appears. It may be shaped by deeper symmetries and hidden dimensions that usually remain concealed. Loop quantum gravity moves along a different path, proposing that space itself may have an underlying discrete structure, built from tiny units woven together in a network. In that picture, smooth space is more like a large-scale impression, the way a shoreline looks continuous from far above, even though it is made of countless grains, gaps, and edges. These models differ sharply in method and interpretation, and none is confirmed, yet both point toward the same strange idea. The familiar fabric of reality may not be basic, it may be a later appearance. If space-time emerges, then the earliest universe may not be describable as a conventional moment located at the start of a conventional timeline. It may instead be a transition from a pre-geometric condition, a state in which distance and duration are not yet meaningful in the ordinary sense. That thought has a quiet but enormous consequence. A beginning may exist without being the first event in time. The origin of the universe may be more like the origin of time than an event inside it. What appears from within the universe as a first instant might be, from a deeper perspective, the point where the concepts of before and after finally become available. This makes the beginning harder to imagine, but it also explains why it remains so resistant to ordinary explanation. Causality, after all, depends on sequence. If sequence itself is still condensing into existence, then cause cannot behave in the usual way. This collapse of ordinary causality is one of the most unsettling features of the Planck frontier. In normal reasoning, every event is explained by earlier conditions. Fire follows ignition, motion follows force, collapse follows instability. But this chain only works inside a background where time already orders events into a line. Near the beginning, that line may no longer be present. Some candidate models suggest that the universe could arise from a bounce, where a prior contracting state reaches extreme density and then reverses into expansion. Others propose that the earliest moment is not a singular point of infinite breakdown, but a boundary smoothed by quantum effects. Some versions of quantum cosmology describe the early universe through a wave function, meaning that it is not initially a single classical history at all, but a spread of possible geometries that only later resolve into a space-time that appears definite. In each case, explanation changes character. It no longer resembles one event pushing another forward through time. It becomes more like a relation between conditions, constraints, and allowed forms of emergence. The singularity itself, long treated as the dramatic heart of the Big Bang, becomes less like a real object and more like a sign that the theory has been pushed beyond its range. In classical general relativity, tracing the expanding universe backward seems to lead toward a state of infinite density and zero size. But infinities in physics often indicate not a true feature of reality, but the failure of a model. Just as older theories break down inside the atom or near the speed of light, relativity may break down when curvature grows too intense, and quantum effects can no longer be ignored. The singularity is therefore both a landmark and a warning. It marks the place where known theory points toward an origin. It warns that known theory cannot be trusted all the way to that point. The beginning appears in the equations as an abyss, but that abyss may be the shadow cast by incomplete understanding. Observations from the later universe keep pressing this mystery from another direction. The cosmic microwave background preserves tiny temperature variations that reflect ancient fluctuations in the density of matter and energy. These patterns are extraordinarily informative. They reveal a young universe that is nearly uniform yet not perfectly so, smooth enough to be puzzling and uneven enough to seed all later structure. Large surveys of galaxies show the imprint of those early fluctuations expanded across billions of light years. The universe remembers its first instabilities, but what generates them? Inflation offers one answer: by stretching microscopic quantum fluctuations to cosmic scales. That answer is elegant and widely studied, yet it still relies on assumptions about the physics operating before ordinary matter forms. It reaches toward the Planck frontier without fully crossing it. The source of the seeds is described, but the stage on which they first appear remains partly veiled. This is where the beginning stops looking like a single explosive event and starts looking like a boundary between two kinds of reality. On one side lies the universe as later physics can describe it, expanding, cooling, forming particles, atoms, stars, and galaxies. On the other side lie something more obscure, where geometry may be quantized, where time may not flow in the normal sense, where causality may be emergent, and where the distinction between existence and possibility is less stable than it seems from within the mature cosmos. It is tempting to treat that obscurity as a simple gap in knowledge that future equations will cleanly fill. Perhaps that will happen. A successful theory of quantum gravity may one day translate these mysteries into a precise and testable structure. Yet even that hope carries a deeper uncertainty. A complete mathematical account of the first physical state would still leave open the question of why such a structure exists at all. So the Planck frontier does not merely hide details. It changes the meaning of the search. It suggests that the earliest universe is not just a hotter version of the later one, but a radically different order of reality. Matter has not yet settled. Space may not yet be smooth. Time may not yet be a line, because may not yet run forward in any familiar way. The universe, at that depth, is not a place where known things behave strangely. It is a threshold where the known things themselves may not yet exist. And in that threshold, the oldest question becomes difficult to phrase without distortion. What came before the Big Bang assumes there is a before. Why did the universe begin assumes beginning is the right kind of event. What caused reality assumes cause still operates where time is not yet secure. The closer the search moves to the source, the more language itself starts to feel like a later invention, useful in the world that follows, but uncertain at the edge where the fabric of that world is only just beginning to become real. The universe does not only conceal its beginning in the past, it may also hide it in the future. This possibility begins with a simple and almost bleak observation. The cosmos is changing in a direction that appears irreversible. Galaxies on the largest scales are moving away from one another as space expands. The expansion is not slowing under gravity in the way once expected. It is accelerating. The farther the future unfolds, the lonelier each region of the universe becomes. Distant galaxies slip beyond one another's observable reach. Starlight thins. Gas is consumed or scattered. The brilliant, crowded era in which stars are born in abundance is not permanent. It is a passing chapter. The universe of the far future is expected to be darker, colder, emptier, and less eventful than the one now visible. This seems at first like a story only about endings. Then the resemblance to the beginning starts to appear. In the present age, the sky is rich with structure. Galaxies spiral and merge. Clusters gather hundreds or thousands of galaxies into great gravitational cities. Nebulae glow with new stars. Supermassive black holes stir the cores of galaxies. Yet this abundance depends on a temporary balance. Stars shine because gravity compresses matter into hot fusion. That process cannot continue forever. Every star lives by spending stored fuel, and each spends it at a different pace. Massive stars burn fiercely and die quickly. Smaller stars survive for far longer. Red dwarfs, the quiet and common stars of the cosmos, may endure for spans so vast that the entire present age of galaxies looks brief beside them. But even they do not escape the arithmetic of exhaustion. Over immense intervals, star formation slows as raw gas becomes locked inside dim remnants or driven away. One by one, the furnaces go out. The night does not arrive suddenly. It deepens slowly, almost invisibly, until brightness itself becomes rare. This expected future is sometimes called heat death. Though the phrase can mislead, it does not mean the universe becomes hot enough to die. It means usable energy becomes so thinly spread that organized activity dwindles. Differences flatten. Structures lose access to the gradients that sustain change. In thermodynamic terms, entropy rises. In ordinary language, the universe grows tired, not in any living sense, but in the sense that fewer things remain able to happen. The stars fade, white dwarfs cool, neutron stars lose heat, brown dwarfs drift in darkness. The largest surviving objects may be black holes, patient and almost impossible to disrupt. Even galaxies themselves begin to lose their central meaning, as expansion isolates gravitationally bound islands from one another. In a very distant future, an observer inside one remnant galaxy could look outward and find almost nothing. The great extragalactic universe would have slipped beyond the horizon of observation. The evidence for cosmic history would be fading from view. That loss matters because it turns the end of the universe into something eerily like the beginning. The earliest observable universe is simple, smooth, and dominated by radiation and elementary conditions rather than rich structure. The far future may also approach simplicity, though by a different route. Complexity thins out, temperature drops, matter becomes sparse. Distances lose ordinary meaning because so little remains in communication with so little else. A strange symmetry begins to suggest itself. The universe starts in a hot, dense, nearly featureless state, and may end in a cold, diffuse, nearly featureless state. At first these seem like opposites. One is full of compressed energy. The other is drained of useful energy. One is bright beyond imagination. The other is dark beyond imagination. Yet both are states where ordinary structure is absent or largely erased. Both sit at the edges of what a lived cosmos can be. This resemblance is one reason some cosmologists begin to wonder whether the deeper secret of the beginning lies not behind the past, but hidden inside the logic of the ending. Black holes stand at the centre of that suspicion. They're among the strangest objects known, regions where gravity becomes so intense that escape is cut off beyond the event horizon. They swallow matter, distort time, and preserve a troubling tension between relativity and quantum theory. For a long time, black holes seem like the final vaults of the cosmos, the places where information and matter disappear into extreme darkness. Then, a surprising quantum result changes their role. Stephen Hawking shows that black holes are not completely black. Through quantum effects near the horizon, they radiate. The radiation is extraordinarily weak for large black holes, but over unimaginable timescales it matters. Black holes slowly lose mass. Eventually, if given enough time, they evaporate. This discovery changes the emotional geometry of the far future. A universe that seems destined to collect more and more matter inside black holes does not end with black holes lasting forever. Even they are temporary. The gigantic black holes at galactic centers, swollen by ages of mergers and accretion, eventually radiate away. What remains after their disappearance is stranger than the present mind easily accepts. If stars are gone, planets frozen, matter decayed or trapped in remnants, and black holes themselves finally evaporated, then the universe approaches an almost pure emptiness filled mostly with thin radiation and enormous silence. It is not absolute nothing. Space remains. Fields may remain. Low-energy particles may remain. Expansion may continue. But the cosmos becomes so empty that the distinction between physical existence and near absence starts to blur. That is where the end begins to lean toward the beginning. Roger Penrose, among others, notices a mathematical hint hidden in this transformation. In ordinary life, size matters deeply. A mountain and a grain of sand are not the same. A galaxy and an atom are not interchangeable. Yet certain physical descriptions become less sensitive to scale under extreme conditions. In a universe emptied of massive particles, where only radiation effectively remains, the significance of size begins to loosen. Radiation does not experience time in the same way massive objects do. A photon crossing the cosmos has no internal clock-marking duration in the ordinary sense. In a universe stripped down to massless content and smooth geometry, some of the distinctions that dominate the structured middle age of the cosmos begin to fade. Penrose sees in this an astonishing possibility. The cold, stretched, almost empty future of one cosmic era may be mathematically transformable into the hot, dense beginning of another. This is not a claim that the far future suddenly explodes or literally contracts back into a small ball. It is subtler, stranger, and harder to picture. The idea suggests that if all massive structure eventually disappears and only a nearly featureless bath of radiation and geometry remains, then the universe may reach a condition where the difference between infinitely large and infinitely small stops carrying its usual meaning. Under a conformal rescaling, which changes size while preserving certain structural relationships. The end state and a new beginning can be related. From inside the structured universe, this sounds almost absurd. Hot and cold are not the same. Dense and empty are not the same. Young and ancient are not the same. Yet at the extremes, when the ordinary anchors of matter, scale, and time have fallen away, those oppositions may not be as absolute as they seem. Even without accepting that proposal in full, the far future remains unsettling. The universe may not die in a dramatic collapse or tearing catastrophe. It may instead fade into a condition so stripped of structure that it becomes conceptually adjacent to an origin state. This does not prove that a new universe emerges. It does not show that one cosmic age becomes another, but it makes the possibility less arbitrary. The future already contains real processes that erase complexity, dissolve massive objects, and reduce the cosmos toward a sparse and nearly timeless condition. The same physics that allows black holes to vanish also suggests that permanence is rarer than it appears. Matter is temporary. Stars are temporary. Galaxies are temporary. Even the darkest vaults of gravity are temporary. When enough temporary layers are peeled away, what remains begins to resemble not the rich middle of the cosmic story, but one of its edges. This is why the end cannot be treated as a separate problem from the beginning. A universe that expands forever into greater emptiness does more than drift toward extinction. It raises the possibility that emptiness itself is not inert. It may be a bridge, a disguised threshold, a state whose full significance only appears when matter and structure have been removed. The earliest universe once seemed unique because it is so hot and dense. The far future once seemed unique because it is so cold and empty. Now they begin to look like reflections across a hidden symmetry. One is the maximum compression of a cosmic story. The other is its maximum dilution. Yet both may lie outside the ordinary scale-bound world where size, duration, and material complexity dominate understanding. So the universe now appears suspended between two strange shores. Behind it lies a beginning that may not be simple creation, but the emergence of structure from a deeper condition. Ahead of it lies an ending that may not be final extinction, but the quiet removal of structure until another condition becomes possible. The stars between these shores burn brightly for a time and make the cosmos feel stable, inhabited, and complete. But they may be only the brief illuminated middle of a much larger pattern. If so, then the dark future is not just the death of the universe. It is a clue. It suggests that what comes after everything may bear a hidden kinship to what comes before anything, and that the strangest feature of cosmic history may be this: the farther the universe moves toward nothingness, the more that nothingness begins to look like the doorway through which reality enters once again. The idea of a cyclic universe appears at first like an attempt to soften the shock of a beginning. Instead of one absolute first moment, there is a pattern. Instead of creation from nowhere, there is recurrence. The universe does not burst into existence once and then move toward a final silence. It expands, cools, empties, and then somehow begins again. This thought is ancient in spirit, but modern cosmology gives it new forms and sharper edges. It is no longer only a philosophical comfort or a mythic image of repetition. It becomes a technical possibility emerging from specific problems in gravitational theory, thermodynamics, and the strange mathematics of the universe at its extremes. Yet the more closely the cyclic idea is examined, the less it resembles a simple wheel turning in familiar time. It becomes something more unsettling. The cycles may not follow one another the way seasons follow one another. They may not even be arranged on a single timeline. What repeats may be reality itself, while the meaning of before and after changes from one cosmic era to the next. Older cyclic models often imagine expansion followed by contraction. The universe grows, slows, reverses, and collapses into a big crunch. From that collapse, a new expansion begins. In its basic form, the picture is symmetrical and easy to grasp. A cosmos breathes in and out. But modern observations complicate this version severely. The accelerating expansion of the universe, inferred from distant supernovae and supported by later measurements of cosmic structure and background radiation, suggests that the cosmos is not on track to recollapse in any simple way. Dark energy, whatever its underlying nature may be, appears to pull the large-scale universe toward continued expansion rather than reversal. This weakens the most straightforward bounce models, or at least forces them into more elaborate forms. The universe does not seem eager to fall back into a single dense state on its own. If a cycle exists, it may have to be stranger than a cosmic inhale after a cosmic exhale. Some theories respond by moving the bounce deeper into the hidden physics of the very early universe. In these accounts, a prior cosmos may contract, but quantum gravity effects prevent a true singular collapse. When density becomes extreme, some new behavior takes over and turns contraction into expansion. Loop quantum cosmology explores this kind of possibility, suggesting that space-time itself may resist compression beyond a certain point because of its discrete underlying structure. Instead of ending in an infinite singularity, the contracting universe reaches a minimum scale and rebounds. The present expanding cosmos would then be the aftermath of an earlier phase. This picture preserves an intuitive cyclic rhythm, but it also introduces a quiet fracture into ordinary thinking. The beginning ceases to be the absolute start of all things, it becomes a transition. The birth of this universe is recast as the memoryless continuation of something older, with the most important event hidden at densities no later observer can inspect directly. That alone would already make the Big Bang less absolute than it first appears. Yet conformal cyclic cosmology goes further by altering not just the mechanism of recurrence, but the very language in which recurrence is described. In this view, the remote future of one cosmic age and the hot beginning of the next are connected not through a conventional collapse, but through a transformation of geometry in which size stops mattering in the normal way. The proposal begins with a striking insight. The young universe near the Big Bang is hot, dense, and filled mostly with radiation rather than stable complex structures. The far future, after stars die, black holes evaporate, and matter becomes either vanishingly sparse or no longer relevant in the same way, may also approach a condition where only radiation effectively remains. In both limits, mass loses its ordinary dominance. If mass is absent or negligible, scale itself may lose physical significance. What seems enormous from one perspective and tiny from another may belong to equivalent descriptions once the usual anchors of measurement have dissolved. This is the core of the conformal idea. The end and the beginning are not the same in the everyday sense, but they can be related by a change in how geometry is represented. One cosmic era, called an aeon in this framework, expands toward extreme emptiness. Then, under conformal rescaling, that final state can be matched to the initial state of a new aeon. The universe does not need to crunch back into a dense point. It only needs to become empty enough, simple enough, and stripped enough of massive structure that the distinction between very large and very small loses physical force. The next beginning does not erupt out of ordinary debris. It emerges from the exhausted geometry of the previous cosmos. That makes the cycle far more eerie than a simple bounce. It does not resemble repetition in time. It resembles repetition through the disappearance of time's usual scaffolding. In such a picture, the Big Bang remains real, but it no longer stands alone. It is the visible opening of the current aeon, while another aeon stretches invisibly behind it. The universe has a history before the history now measured, yet that prior history is not earlier in a simple chronological sense, because the timeline of one aeon does not extend smoothly into the next, like a single uninterrupted road. Each aeon has its own internal time. The transition between them is more abstract. It is grounded in geometry and physical conditions rather than in an event that an observer could watch from outside. This is where the cyclic idea becomes genuinely unsettling. A previous universe may exist without leaving behind an ordinary past. It may contribute to the present without standing in familiar temporal relation to it. The current cosmos would then be born from something real that cannot easily be called earlier in the common sense of the word. The speculative power of this view increases because it does not remain purely philosophical. It invites the search for traces. If a previous aeon influences the beginning of this one, perhaps some faint scars survive in the cosmic microwave background. The afterglow released when the young universe first becomes transparent to light. Penrose and collaborators have argued that unusual patterns in this radiation, including concentric features or anomalies in temperature distribution, may be interpreted as signs of violent events in the preceding aeon, such as collisions involving supermassive black holes. These claims are controversial. Other researchers have challenged both the statistical methods and the interpretation of the data. No consensus has been reached. Yet the very fact that such a search is possible changes the tone of the question. What came before the Big Bang is no longer treated only as a metaphysical abyss. It becomes, at least in principle, a subject that might leave faint observational fingerprints, even if those specific signatures do not survive scrutiny. The broader logic of cyclic cosmology continues to pull at the imagination of physics. A repeating universe offers something that a one-time creation struggles to provide. It reduces the need for a completely uncaused first event. If each cosmic phase arises from features of the one before it, then the burden of explanation is distributed rather than concentrated into a single impossible instant. The universe becomes self-linked across eras. One reality hands structure to the next, even if that handoff occurs through mechanisms that stretch the meaning of causation. This gives cyclic theories a certain elegance. They do not erase mystery, but they keep mystery moving instead of letting it pool in one absolute origin. Yet this elegance comes with its own unease. A cycle without a first moment may seem satisfying at first, but it raises new problems almost immediately. Does entropy increase across cycles? And if so, why does the universe not simply run down permanently? If the cycles differ, what determines the variation? If they repeat identically, what makes identity possible across transitions where time and scale are being reformulated? If each aeon inherits something from the last, what exactly is preserved? Geometry, information, statistical structure, quantum possibilities? No answer is settled. Some versions imply novelty from one cycle to the next. Others imply a deeper recurrence. Still others suggest that the cycle may not repeat in a fully temporal sense at all, but rather that the universe occupies a self-connected structure in which beginnings and endings are linked from outside ordinary chronology. This is where cyclic cosmology begins to overlap with the mystery of emergence itself. A universe with no first moment is not necessarily easier to understand than a universe with one. In some ways it is harder. It removes the sharp wound of a first beginning, but in return it asks the mind to accept a reality that sustains itself through transformations more radical than birth and death. The present cosmos becomes only one phase of a broader pattern, and the Big Bang becomes less like a unique miracle and more like a recurring threshold where the visible world is repeatedly reconstituted from conditions that no observer can fully inhabit. The cycle offers continuity, but not comfort. It explains beginnings by turning them into reappearances, then leaves open the deeper question of why the pattern exists at all. So the universe now stands in a new light. The beginning may not be a wall beyond which thought cannot pass. It may be a seam. Behind it there may be another cosmic age, and behind that another still, whether through bounces, rescaled aeons, or some structure not yet imagined clearly. The Big Bang would then be a local name for a recurring transition inside a reality far older than the visible sky suggests. Matter forms, stars burn, galaxies gather, darkness spreads, structure dissolves, and then somehow the hidden conditions for another beginning gather again. The cycle is not confirmed. It may prove false, but it persists because it takes seriously a possibility that the universe itself seems reluctant to dismiss that endings and beginnings are not opposites, but neighbouring faces of the same deep process, and that what lies before the Big Bang may not be nothing at all, but the exhausted remains of another world waiting, in a form almost beyond recognition, to become real once more. The mystery changes again when the universe is no longer treated as the whole of reality, but as one region, one branch, or one outcome inside something larger. This idea does not begin as fantasy. It emerges from pressure points inside real physics, places where well-tested theories seem to widen beyond the single world that common sense expects. Quantum mechanics is one source of that pressure. Cosmic inflation is another. Together they open a door that many physicists approach with caution and that many others resist outright. Yet the door remains difficult to close. If the mathematics is taken seriously in certain ways, then the Big Bang may not be the solitary birth of everything. It may be the local beginning of this universe only, while countless other realities unfold alongside it, beyond it, or beneath it. Quantum mechanics first introduces the problem at the smallest scales. In that realm, physical systems are not always described as having one definite state before measurement. They are described by superpositions, combinations of possibilities that evolve according to strict mathematical rules. An electron can be associated with several potential outcomes at once. A photon can travel through different paths in a way that does not fit ordinary logic until an observation fixes a result. The theory works with extraordinary accuracy. Its predictions power modern electronics, lasers, atomic clocks, and much of present technology. Yet what the theory means remains unsettled. Does the world truly remain indefinite until measurement? Does the wave function merely represent incomplete knowledge? Or do all allowed outcomes continue, each realized in a different branch of reality? This last idea, often called the many worlds interpretation, is not an extra fantasy placed on top of quantum theory. It is one reading of the existing mathematics, a reading in which the equations are left to unfold without collapse. If that interpretation is taken seriously, then reality is not a single line of events, but a continually branching structure. Every quantum event that permits several outcomes does not select one and discard the rest. Instead, all outcomes are realized, each in its own branch. Most of these branches are not dramatic alternate worlds where history veers wildly at every moment. They're often almost identical except for tiny differences. But over time, small divergences can grow into larger ones. In some branches, a star system forms one way, in others, slightly differently. In some, a world remains barren. In others, life appears. In some, the cosmic story unfolds close to the one known. In others, it drifts into unfamiliar possibilities. This view is difficult to test directly and difficult to imagine cleanly. Yet it carries a striking implication for origins. The universe may not come into being as one singular realized outcome. It may be born already as a vast quantum structure containing many coexisting histories. That alone is unsettling enough, but inflation stretches the idea further. In many inflationary models, the early universe undergoes a brief period of exponential expansion, driven by a high-energy field state. In some versions, this process does not stop everywhere at once. It ends in one region while continuing in others. Local pockets settle into expanding universes with their own hot beginnings, while the larger inflationary background keeps generating more such pockets. This picture is often called eternal inflation. The name sounds dramatic, but the underlying logic is simple. If the inflationary field decays unevenly and quantum fluctuations keep parts of it from ending uniformly, then universe-producing regions can continue to form again and again. Each bubble universe may have its own conditions, its own pattern of symmetry breaking, perhaps even its own effective constants or particle content depending on the deeper framework involved. The Big Bang, in that setting, is not the first beginning. It is one local ignition in an endlessly fertile cosmic landscape. The multiverse then appears in more than one form at once. One version comes from quantum branching, another comes from inflationary bubble creation. A third emerges in some interpretations of string theory, where a vast landscape of possible vacuum states may allow different universes to settle into different laws. These are not identical ideas, but they often overlap in public imagination because they all enlarge the background beyond the visible cosmos. The universe becomes less like a totality and more like an instance. This has a profound effect on the old question of what came before the Big Bang. The answer may no longer be another phase of this same universe, as in cyclic models. It may be a deeper environment in which many universes continuously arise, branch, or coexist. The beginning then belongs to one world, not to all worlds. This change can explain certain puzzles, though never without cost. The fundamental constants of nature appear finely tuned for structure. The strength of gravity, the masses of particles, the balance of forces, and the properties that govern atomic stability and stellar burning all fall inside narrow ranges that allow complex chemistry, long-lived stars, and the slow construction of galaxies and planets. One response is to treat this tuning as a brute fact. Another is to hope that a future theory will show these values had to be what they are. But a multiverse offers a different answer. If there are many universes with different conditions, then it is not surprising that at least some permit complexity. Observers naturally find themselves in one of those. The explanation is statistical rather than singular. Reality generates many cosmic combinations, and conscious life appears only where the settings happen to allow it. This does not prove the multiverse. It does, however, show why the idea remains attractive. It turns apparent coincidence into selection. Yet this attraction is also what makes the multiverse deeply controversial. A theory that explains almost anything by saying that all possibilities occur somewhere risks explaining too much. If every outcome exists in some branch or some bubble, what would count as disproof? How does one distinguish scientific widening from metaphysical escape? These objections are serious. Many physicists worry that multiverse reasoning loosens the bond between theory and observation too far. Others reply that if the best explanations of observed data naturally imply a larger unseen reality, then refusing that implication simply because it is difficult to test would be intellectually timid. The tension remains unresolved. The multiverse sits in a region where physics, interpretation, and caution intermingle. Even so, the visible universe occasionally offers hints, or at least temptations. Some researchers have looked for unusual patterns in the cosmic microwave background that might betray a past collision between our bubble universe and another. A collision of that kind, if it occurred in the early inflationary era, might leave a circular or directional anomaly in the background radiation. Claims of such features have appeared and then faced strong criticism. None has become accepted evidence. Similarly, Large-scale anomalies in the microwave background, such as asymmetries or curious alignments, have inspired speculation about structures beyond the observable horizon. Most of these patterns remain ambiguous. They may be statistical flukes, artifacts of data handling, or natural results of known processes. Yet their persistent appearance in discussion shows something important. The universe is not only measured, it is read for traces. Observers keep asking whether the sky contains the bruises of contact with something beyond itself. The multiverse also changes the emotional meaning of the Big Bang. In a single universe picture, the beginning carries an absolute weight. Everything depends on one first physical state. In a multiverse picture, that weight is distributed. This universe still has a beginning, but its beginning does not bear the full burden of existence. It may emerge from a branching quantum history, a parent inflationary medium, or a vacuum landscape already full of unrealized possibilities. The old question then shifts. Instead of asking why this universe exists rather than nothing, one asks why the larger generative framework exists rather than nothing. The mystery is not removed. It is displaced outward into a deeper layer. The Big Bang becomes less final as an explanation and more local as an event. There is another subtler consequence. If many universes exist, then what counts as law may need to be reconsidered. The laws observed here may not be ultimate. They may be environmental, the local expression of a deeper reality that permits many forms. What appears universal from inside one cosmos may be provincial from a wider view. This is difficult to accept because science has long advanced by finding rules that seem to apply everywhere. Gravity falls the same way on Earth and in distant galaxies. Light behaves with the same speed across the observable universe. Spectra from faraway atoms match those measured in laboratories. Uniformity is one of the triumphs of modern physics. But the multiverse whispers a more unsettling possibility. Uniformity may hold magnificently within one bubble of reality, while other bubbles obey different settled conditions altogether. The visible order would remain real, but it would no longer be the whole story. In that light, what came before the Big Bang becomes stranger than another universe in time or another cycle in sequence. It may be a realm in which many beginnings are ordinary, where universes are not rare exceptions but recurrent expressions of a deeper generative background. It may be a branching quantum totality in which this cosmos is one realized thread among countless others. It may be a cosmic landscape in which physical law itself crystallizes differently from one domain to another. None of this is confirmed. Much of it may prove wrong. But the possibility cannot be dismissed as easily as it once could, because it grows not from idle invention, but from the honest extension of theories already trusted in narrower domains. The result is unsettling in a very specific way. The Big Bang no longer looks like the unique door through which all reality enters. It looks like one door in a structure too vast to see, opening into one habitable chamber among many, while beyond its walls other beginnings burn unseen in the dark. The universe becomes even harder to place when its behavior is viewed through the two great habits of modern physics that seem, at first glance, to point in opposite directions. One habit is order, the other is uncertainty. One says that reality unfolds by law with exquisite regularity, that given the right description of a system and the forces acting on it, its evolution can be traced with confidence. The other says that, at the deepest level, certainty gives way to probability, and that physical events are not always fixed in advance in the clean mechanical sense that older science once imagined. Both habits are real. Both are grounded in observation. Both have built astonishingly successful theories. Yet when the question turns toward the origin of the universe, the tension between them stops being an abstract technical concern and becomes central to the mystery itself. If the universe began, Did it begin as the inevitable consequence of law, or as the realization of one possibility among many? If there was something before the Big Bang, was it governed like a clock or unsettled like a quantum wave? And if both order and uncertainty are woven into reality from the start, then what kind of beginning can contain them together? On the larger scales, the universe appears deeply lawful. Galaxies form filaments and clusters according to gravity. Light bends around massive bodies with exactly the kind of grace described by general relativity. Planetary orbits follow predictable paths. Stars live through stages that can be modelled from their mass and composition. Even the expanding universe itself is not chaotic in any loose sense. Its large-scale evolution follows equations that relate density, pressure, curvature, and expansion. The cosmos is not random noise. It is structured, patterned, and intelligible. This is why science works at all. It works because nature does not reinvent its rules from moment to moment. The same kinds of causes produce the same kinds of effects. The same physical constants appear in distant galaxies and nearby laboratories. This regularity gives the universe a deterministic face. It suggests that whatever else reality may be, it is not arbitrary. This deterministic face becomes especially impressive when the universe is simulated backward and forward in time, starting from the tiny irregularities seen in the cosmic microwave background. Cosmologists can model how gravity gradually amplifies those small differences into the web of galaxies now observed across immense distances. Structures grow where matter is slightly denser. Voids open where it is slightly thinner. Dark matter deepens the scaffolding. Gas falls into gravitational wells. Stars ignite, and galaxies assemble. The details are complicated, but the broad process is coherent. The mature universe looks like the evolved consequence of simpler earlier conditions. Every success of this kind strengthens the sense that the cosmos is, in a profound way, lawful enough to be read as a continuous unfolding. It invites the old dream that if one knew the initial state perfectly and knew the laws completely, the entire history of the universe would follow in principle. Yet the deeper physics goes, the more that dream begins to crack. Quantum mechanics does not deny order, but it redefines it. The equations governing quantum systems are strict, precise, and deterministic in one sense. The wave function evolves according to law, but the outcomes that observers actually record do not present themselves in the same fixed manner as the trajectories of planets. They come weighted by probabilities. A particle can be described as having a spread of possible positions. A radioactive atom can decay at no exact predictable instant, only with a certain likelihood over time. Photons pass through experimental setups in ways that resist being reduced to one hidden path chosen in advance. The quantum world is not lawless, but its laws govern distributions, amplitudes, and possibilities rather than simple certainties about individual events. This does not merely add randomness to a clockwork machine. It changes the character of what a physical description is. That change matters immensely for origins. If the universe began from a quantum condition, then its earlier state may not have been one fixed classical arrangement waiting to unfold. It may have been a cloud of possibilities, a structured but indeterminate condition from which the later classical universe emerges. Some approaches to quantum cosmology treat the universe itself in this way, describing the beginning through a wave function over possible geometries or field configurations. In such pictures, the universe is not born with every detail pinned down. Its earliest reality is closer to a range of allowed histories than to a single already written script. Later stability, including the familiar solidity of space-time and matter, would then be something that condenses from a more probabilistic foundation. The cosmic story would not begin as a fully defined path. It would begin as a field of potential constrained by law, but not exhausted by one deterministic outcome. This seems, at first, to clash with the orderly appearance of the later universe. But the clash may be more apparent than real. Probability and order do not necessarily cancel each other. Quantum fluctuations in the early universe, for example, are often invoked to explain the tiny differences in density that later become galaxies. Those fluctuations are not random in the careless sense of being structureless. They arise within a lawful quantum framework. Inflation stretches them across cosmic scales, turning microscopic uncertainty into the seeds of large-scale order. The galaxies, then, may owe their existence not only to deterministic gravitational growth but also to primordial quantum variation. The same universe that later follows clear structural laws may therefore depend, at its deepest visible roots, on fluctuations that are probabilistic in character. Order emerges, but it emerges from a field of uncertainty that is disciplined rather than chaotic. This possibility reshapes the meaning of a beginning. A deterministic beginning suggests inevitability. Given the initial state, this universe had to happen as it did. A probabilistic beginning suggests contingency. The laws permit a range of outcomes, and this universe is one realization among them. Neither view is simple. Pure inevitability makes the universe feel rigid, almost frozen by necessity before it begins. Pure contingency makes it feel fragile and difficult to explain, as though existence hangs on cosmic chance. The actual situation may be more strange than either extreme. The laws may be deterministic at one level and probabilistic at another. The early universe may evolve lawfully while still containing genuine distributions of possible outcomes. This would mean that reality is neither a script nor a lottery in the ordinary sense. It is a constrained field of becoming, where some features are fixed by deep structure and others arise through probabilistic unfolding. The problem grows sharper when the origin of physical law itself is considered. Determinism assumes laws that govern events. Probability also assumes laws, though of a different kind. But if the question is not merely how the universe evolves, but why there is a universe with these laws at all, then both approaches run into the same wall. A deterministic model can describe how a given state leads to later states. A probabilistic model can describe how outcomes are distributed across possibilities. Neither automatically explains why there is a lawful framework in the first place. The deeper the search goes, the more both order and uncertainty begin to look like features of a pre-existing structure. They may differ in how they govern events, but they both still require a stage on which governance can occur. At the origin, this creates a profound unease. Was law already there before the universe in its present form? Did probability already apply before space-time settled into being? Or are both law and chance emergent properties of a still deeper order that no current theory fully describes? This is where the idea of a final unifying framework, sometimes called a theory of everything, begins to exert its pull. The phrase is often misunderstood. It does not promise to explain every detail of history, weather, biology, or thought in a trivial sense. It points instead toward a deeper set of principles capable of uniting the currently separate descriptions of the large and the small, the gravitational and the quantum, the deterministic and the probabilistic. Such a theory would not necessarily make the universe simpler to imagine. It might make it stranger. But it could reveal how the apparent opposites of order and uncertainty fit inside one larger logic. Perhaps space-time itself emerges statistically from a more fundamental quantum structure. Perhaps what looks probabilistic inside the universe reflects a deeper deterministic process outside ordinary space-time. Perhaps what looks deterministic at macroscopic scales is the stable average of deeper fluctuations. Many possibilities remain open. What matters is that the tension between necessity and chance may be a sign of incomplete perspective, rather than a final contradiction. The search for such a unification continues because the universe keeps behaving as though these two faces belong together. Quantum theory governs the microstructure of matter. Relativity governs the architecture of the cosmos. Black holes demand both. The early universe demands both. The origin of structure from tiny fluctuations demands both. Every time physics approaches a threshold where beginnings matter, certainty and uncertainty appear side by side like twin signatures of a deeper reality. One supplies continuity and law. The other supplies variation and openness. One makes the universe intelligible. The other makes it creative. Neither alone seems sufficient to account for the full story. This matters because the question of what came before the Big Bang may depend less on choosing between determinism and probability than on understanding why the universe contains both. A prior state might not be a simple mechanical engine ticking toward a fixed outcome, nor might it be a formless haze of arbitrary possibility. It may be something that already combines strict structure with genuine openness, a reality in which laws constrain what can happen, while probabilities govern which allowed paths are realized. The beginning of this universe would then be neither fully scripted nor fully accidental. It would be the emergence of one coherent cosmos from a deeper domain, where necessity and possibility are not enemies, but companions. In that light, the universe looks less like a solved equation and more like a carefully balanced tension. The stars and galaxies display order. The quantum vacuum displays fluctuation. The background radiation preserves statistical patterns born from early uncertainty. Gravity amplifies those patterns into stable structure. Life and thought arise in a cosmos that is lawful enough to endure and indeterminate enough to generate novelty. The oldest question remains open because both of reality's great tendencies point beyond themselves. Determinism alone cannot explain why this lawful structure exists. Probability alone cannot explain why possibilities are organized at all. At the beginning, each reaches for the other, and so the mystery deepens once more. Whatever lies before the Big Bang, if anything can be said to lie before it, may be neither a perfect machine nor a perfect accident, but a deeper order in which law and chance are born together, long before the first atoms, long before the first light, and perhaps even before time learns how to move. The universe does not only withhold its deepest answers, it also leaves behind patterns that look, for brief moments, as if they might reveal too much. This is one reason cosmology never settles into pure confidence. The broad picture is strong, yet the details are restless. Every time instruments improve, the cosmos offers not only sharper agreement with theory, but also subtle irregularities, disputed signals, mismatched values, and structures that seem to lean just slightly away from expectation. Most of these tensions eventually find ordinary explanations. Some vanish when methods improve. Some remain unresolved for years without becoming revolutionary. Yet together they create an atmosphere that matters. They remind science that the universe is not fully domesticated, and that the path back toward the beginning may be marked not by one dramatic contradiction, but by a scattered trail of anomalies too small to ignore and too uncertain to trust completely. The cosmic microwave background is one of the clearest examples. It is often described as the afterglow of the early universe, a nearly uniform bath of radiation spread across the whole sky and cooled by expansion to microwave wavelengths. Missions such as Wilkinson, microwave anisotropy, Probe and Planck measure this background with extraordinary precision, revealing temperature variations so tiny that they seem almost beyond significance. Yet those minute differences are among the most important structures in science. They contain the seeds of all later cosmic architecture. They show where matter is slightly denser, where gravity will later gather gas and dark matter into galaxies, and where emptier regions will open into the vast voids between clusters. In most respects, the map fits the standard cosmological story with remarkable elegance. But it also contains peculiar features that continue to attract attention. Certain large-scale patterns appear unexpectedly aligned. Some hemispherical asymmetries seem stronger than naive expectations suggest. A region known informally as the cold spot appears unusually pronounced. None of these features alone proves new physics, yet each one tempts the mind toward a difficult possibility. The oldest light in the universe may carry hints of processes not fully captured by the simplest account. The cold spot is especially haunting because it behaves like an unfinished clue. It is a broad region of the microwave background cooler than surrounding areas by a margin large enough to provoke years of debate. One explanation suggests that light passing through an enormous underdense region of space could lose energy in a way that contributes to the effect. Another possibility is that it is simply a rare statistical fluctuation, unusual but not impossible in a universe this large. More speculative suggestions have tied it to traces of a collision between our universe and another bubble in a wider inflationary setting. That last idea remains far from established, and many researchers reject it. Yet the fact that it can even be entertained shows how thin the border has become between data and deeper speculation. A single abnormal patch in ancient radiation is enough to reopen questions about the boundaries of reality itself. Another unsettled pressure comes from the expansion rate of the universe. When astronomers estimate the present rate of cosmic expansion by observing nearby supernovae and other local distance markers, they obtain one value. When they infer the same quantity indirectly by fitting the early universe data from the cosmic microwave background within the standard cosmological model, they obtain another. The disagreement is not enormous, but it is persistent enough to become one of the most discussed issues in present cosmology. This tension may eventually be traced to hidden systematic errors, unrecognized details in measurements, or improved calibration. It may also hint that the standard model of cosmology, successful though it is, misses some ingredient linking the early universe to the later one. If so, that missing ingredient could reach all the way back toward the first moments. The present expansion and the ancient afterglow would then be quietly signaling that the history joining them is not as simple as once thought. Dark matter deepens the sense of incompleteness in a different way. Galaxies rotate too quickly at their edges to be held together by visible matter alone. Clusters of galaxies bend light and move as though far more mass is present than telescopes can see. Large-scale structure forms in ways that strongly suggest an invisible gravitational scaffold, yet after decades of effort. Dark matter has not been directly identified in laboratories. It appears everywhere by influence and nowhere by direct sight. It behaves like substance and remains stubbornly absent as a known particle. This creates an unnerving condition. The universe seems to rely on a hidden mass component for its structure, including the early growth of galaxies from primordial fluctuations, but the true identity of that component remains unknown. Every origin story must therefore be told inside a cosmos whose architecture depends heavily on something still unseen. Dark energy is even more elusive. Observations of distant supernovae, supported by later measurements of cosmic structure and background radiation, indicate that the expansion of the universe is accelerating. Something on the larger scales acts against gravity's tendency to pull matter together. Whether this is vacuum energy, a new field, a modification of gravity, or something even stranger remains uncertain. Its effect dominates the long-term future of the cosmos, yet its nature is obscure. Here the anomaly is not a small irregularity in a dataset. It is a governing feature of the whole universe. Most of the cosmos appears to be driven by something no one can describe with confidence in ordinary physical terms. This matters because any account of what came before the Big Bang must reckon with the possibility that reality is already stranger, even now, than its visible matter suggests. If the universe is mostly made of hidden mass and hidden acceleration, then the unknown is not confined to the beginning. It is active at every scale of the present. Black holes contribute another layer of ambiguity. Their existence is now supported by overwhelming evidence, from stellar remnants to the giant dark objects at galactic centers, and from gravitational wave detections of mergers to direct imaging of event horizon shadows. Yet they remain places where the known laws of physics strain against one another. What happens to information that falls into a black hole remains one of the most severe puzzles in theoretical physics. Does information survive in some encoded form? Is it released in Hawking radiation? Is space-time near the horizon hiding new physics? The problem is not only about the fate of infalling matter, it is about whether the universe fundamentally preserves information or permits a deeper kind of loss. That question echoes origin mysteries because it touches the relationship between quantum theory, gravity, and the fate of physical order under extreme conditions. The same conceptual fracture that appears inside black holes may also appear at the beginning of the universe. There are also the anomalies that may prove to be nothing more than the universe's natural roughness. Large quasar groupings, early massive galaxies, unexpected timing in the growth of cosmic structure, debates over whether some ancient object appear too mature too soon, all drift through cosmology with varying force. James Webb has intensified some of these discussions by finding bright galaxies in very early epochs, prompting arguments over whether galaxy formation begins earlier or proceeds faster than older models assumed. Most likely. Many of these tensions will be softened by better data and better modelling. Yet their cumulative effect remains important. They keep the early universe from becoming emotionally closed. They preserve the sense that the cosmos is still capable of surprise, that even the first billion years after the Big Bang are not fully settled territory. This is the atmosphere in which speculation survives, not because evidence has already overturned the standard story, but because the story, though powerful, remains surrounded by meaningful uncertainty. The universe fits its models beautifully and then leaves odd fingerprints at the edges. Ancient radiation is almost perfect, but not perfectly quiet. Expansion is measured with extraordinary care and still resists clean agreement. Hidden matter shapes galaxies without revealing its face. Hidden energy steers the future without revealing its source. Black holes obey general relativity and still threaten the logic of quantum theory. The cosmos looks decipherable from afar and cryptic up close. So the search for what came before the Big Bang does not proceed in darkness alone. It proceeds through these faint disruptions, these unresolved patterns, these places where measurement becomes strangely suggestive. None may turn out to be the long-sought doorway to a deeper origin, but together they keep the doorway open. They imply that the visible universe may not be fully self-contained in explanation, that the beginning may have left traces not as loud declarations but as subtle misfits in the data, small irregular seams where the deeper fabric almost shows through. And if that is true, then the greatest mystery may not lie in some inaccessible past alone. It may already be scattered across the sky, hidden in the oldest light, the unseen mass, the accelerating void, and the fragile numerical tensions that refuse, year after year, to disappear. By the time the search reaches its deepest point, the question itself begins to come apart. What came before the Big Bang sounds simple, only because ordinary language smuggles ordinary time into a place where time may not yet exist. The phrase assumes a sequence, a waiting period, a background in which one condition can stand ahead of another. But everything learned along the way has been pushing against that assumption. Matter is not present at the start in familiar form. Space is not obviously fundamental. Time may emerge rather than flow eternally, cause may depend on the existence of a temporal order that is still absent at the threshold. Even emptiness is not empty in the way intuition first imagines. By the end of this long descent, the beginning no longer looks like a door opening onto an earlier room. It looks like a change in the very grammar of reality. This is why the oldest answers now seem too small. The universe did not likely arise the way fire starts in dry grass, or the way a star is born from a cloud. Those are events inside a world whose rules and stage already exist. The Big Bang, if it marks the true beginning of this cosmos, is not inside a world like that. It is bound up with the emergence of the stage itself. Space expands, but that expansion may not be into anything. Time begins, but that beginning may not occur at a moment inside some larger timeline. The laws of nature govern the earliest known processes, but those laws may themselves reflect deeper conditions that no present theory fully captures. The closer the mind moves toward the source, the less it finds an event in the ordinary sense, and the more it finds a boundary where the categories used to describe events first become possible. Some possibilities now gather around that boundary. One is that there is no meaningful before at all. In this view, the universe does not arise from a prior temporal state because time itself begins with the earliest physical reality. Asking what comes before would then be like asking what lies north of the North Pole. The question feels natural while still depending on a map that no longer applies. This is a severe answer, but not an empty one. It does not say the beginning is solved. It says the beginning may be the limit of a kind of thought shaped inside the universe and therefore not guaranteed to reach beyond its own foundations. Such a view preserves the Big Bang as a genuine origin, while warning that origin need not mean transition from an earlier state. Another possibility is that the beginning is real, but not singular. The universe may emerge from some prior quantum condition that does not resemble time as later experienced. In this case, there is something before, but not earlier in the familiar sense. A quantum precursor, a pregeometric state, or a deeper field of possibilities could underlie the birth of space-time without sitting behind it on an ordinary timeline. The current universe would then be grounded in something more basic than itself, yet not something that can be neatly called a past universe. This preserves emergence while weakening chronology. Reality would have depth rather than sequence. The Big Bang would be the first visible articulation of a deeper order, not the first existence of anything whatsoever. Then there is the possibility that the beginning is a repetition hidden by transformation. Cyclic models, conformal ideas, and certain bounce scenarios all suggest that this universe may follow another, not through a simple chain of events in the familiar sense, but through a process in which endings and beginnings lose their sharp distinction. The far future empties, massive structure disappears, scale loses force, and a new hot beginning becomes possible. Or a contracting cosmos reaches a quantum threshold and rebounds into expansion. In such pictures, what comes before the Big Bang is not nothing, but a prior cosmic state whose relation to the present is real, even if ordinary cause and effect cannot fully describe it. The beginning remains dramatic, but it is no longer absolute. It becomes the visible hinge of a much older pattern. Beyond that lies the possibility that this universe is not the whole arena, a multiverse, whether born from eternal inflation, quantum branching, or some deeper landscape of allowed states, would transform the Big Bang into a local beginning. This universe would still begin, but reality itself would not begin there. Other universes might branch, bubble, or coexist beyond any observational reach. Some might share similar laws, others might differ in ways too radical for the present mind to picture clearly. The question of what comes before would then point not to the previous moment of this cosmos, but to the larger framework from which universes arise at all. The mystery would not disappear. It would simply widen until the current cosmos looked like one illuminated chamber inside a structure otherwise dark. Each of these possibilities tries to remain faithful to something already glimpsed in real physics. The know-before view respects the dependence of causality on time. The quantum precursor view respects the instability of ordinary space-time near the Planck frontier. Cyclic models respect the strange symmetry between the simplest beginning and the emptiest ending. Multiverse ideas respect the generative excess implied by some readings of quantum theory and inflation. None is arbitrary, none is free of difficulty, and none closes the question. Every model that reaches beneath the Big Bang discovers that the deeper level does not simplify the mystery. It changes its shape and often enlarges it. This may be the strangest part of all. The search does not lead from confusion to clarity in a straight line. It leads from one kind of clarity into another kind of confusion, one that is sharper, more disciplined, and more difficult to dismiss. The early universe is no longer a mythic blur. It is mapped in relic light, chemical abundances, gravitational growth, and the measured expansion of space. The first fractions of a second are not empty speculation. They are partly constrained by evidence and theory. Yet precisely because the known picture is so strong, the remaining darkness feels more significant. The mystery survives not in spite of science, but because science pushes the boundary into a region where the concepts of time, space, matter, and causation begin to fail together. The unknown is no longer a blank at the edges of knowledge. It sits underneath knowledge like a deeper floor not yet reached. That is why the idea of absolute nothing has become so elusive. Every path that tries to locate it finds instead a structured absence, a quantum vacuum, a geometric boundary, a field, a prior state, a statistical landscape, or a mathematical condition in which something is already in place. Even the most minimal beginnings seem to require law, potential, relation, or form. Physics, at least so far, does not encounter a clean void from which being simply erupts. It encounters states that are strange, thin, unstable, and unlike ordinary reality, but still not nothing in the pure sense. This does not prove that true nothingness is impossible. It only shows that the route toward it keeps dissolving into deeper kinds of something. The origin recedes every time it is approached, not because it is empty, but because it is crowded with foundations more subtle than expected, and so the universe comes to rest in a final suspended image. Not conclusion, not a solved beginning, but a threshold held open by evidence and by the failure of evidence to go far enough. Behind the first light lies a hotter darkness. Behind the first atoms lies a storm of unstable particles. Behind that lies a frontier where space-time itself may be unfinished. Behind that may lie a previous aeon, a quantum depth, an eternal branching background, or no before at all. The great mystery does not declare which path is true. It only makes one thing increasingly clear. The Big Bang may not be the ultimate beginning in the simple sense once imagined. It may be the first moment this universe can call its own, while beyond it reality remains older, stranger, and less obedient to everyday thought than any ordinary beginning could ever be. The question remains, not because nothing can be said, but because what can be said keeps pointing toward a source that is not merely hidden in the distant past. It is hidden in the structure of existence itself, where time may be born, where emptiness may already be full, and where the first instant of the cosmos may be less a starting point than the moment the universe finally becomes visible to itself. For all its precision, the universe still keeps its oldest secret close. Telescopes reach deeper into the dark. Satellites map the oldest light. Equations trace the growth of galaxies, the death of stars, the pull of invisible matter, and the strange acceleration of empty space. Yet every answer seems to arrive with a shadow behind it. The first light points to an earlier darkness. The earliest matter points to a prior storm of energy. The structure of space points to something deeper than space. Time itself, which seems so steady in ordinary life, begins to look like a local feature of a much stranger reality. Whether the Big Bang is a true beginning, a transition, a rebound, a branching, or the visible edge of a greater cosmic process, one thing remains unchanged. The universe is not simple at its foundation. It is layered, elusive, and quietly more ancient than it first appears. Perhaps what came before the Big Bang is not a place, not an era, and not a single event waiting to be uncovered, but a level of reality where the usual distinctions between before and after, something and nothing, ending and beginning, no longer hold in the way they seem to now. That possibility does not close the mystery, it deepens it, and in that depth, the cosmos becomes even more beautiful. It is not only vast in size, but vast in uncertainty, vast in hidden structure, vast in the number of questions it can still ask without answering. The stars above belong to a universe that reveals just enough to remain unforgettable, and hides just enough to remain endless. Somewhere behind the first dawn of time, the deeper story waits in silence, patient and unresolved, still beyond the final horizon of thought.